But what is feature scaling and why should we do it? Let's find out. Let's start with a simple linear regression model y equals theta1 x1 plus theta2 x2, where x1 and x2 are features and theta1 and theta2 are model parameters and y is the target variable. The cost function for this problem would look something like this. On one axis there is theta1 and we have theta2 on the other, and the value of cost function j, which is a function of theta1 and theta2, lies on this axis. Now to find optimum value of theta1 and theta2, we start with any random values of theta1 and theta2, then we run gradient descent iteration to update the parameters, and after a lot of steps we finally reach the value of parameters for which cost function assumes minimum. Such a pair of parameters makes this model best linear approximation of the relation between features and target. Now, if you have to visualize cost function in 2 dimensions, we use something called contour plot. On the axis we have parameters and cost represented as circles. Now this is like looking cost function from above. We'll have same value of cost on any given circle on contour plot. And as we go inwards, cost decreases. It decreases to minimum at the center. Now you can visualize gradient descent here as well. We take small steps inwards to reach the minimum. Now let's look at an example. This is height of a person in meters. It lies in the range of 1.5 to 1.8 meters. We also have weight in kgs, and it has a large magnitude comparatively in the range of 55 to 85 kgs. And we have corresponding top speed of that person in meter per second. Let's call height x1 and weight x2 as the features and y, the top speed, as target. Now this is our model. Top speed equals theta1 times height plus theta2 times weight. Can you imagine what its cost function would look like? Boom, pretty flat. Let's understand this. Let's start with theta1, and if we take a step from here to here, the cost function decreases. Now if we take a step of same distance from here to here, we actually passed over the minima because the cost function is squeezed due to uneven magnitude of height and weight. While height is in range of 1.5 to 1.8 meters, weight is in 70s and 80s. If we start implementing gradient descent on this problem, we shall see it inefficiently oscillates around the minimum, particularly when it is closer to it. This makes gradient descent inefficient and slow. On the other hand, if we had something like this, where height and weight are in similar magnitude, through a process called standardization, we can have a cost function like this, which can smoothly descend to minima, which makes it faster and efficient. Now there are various techniques to scale features. One of them, which I used here, is called standardization, where new height is calculated as original height minus mean of heights divided by its standard deviation. And the same way for weights. This technique scales down the variables to have mean 0 and standard deviation as 1. You can also scale features with something called mean normalization, where you can just replace the denominator with maximum of height minus minimum of height, also known as range. There are also other techniques to scale features, but these two are widely used. Now, not only scaling features help us reach minimum of a cost function faster, it also improves performance of certain models. Let's see how. This is a plot of height and weight of a person, and I populated males here. Now let's add some females as well so that it doesn't become mechanical engineering. Now this is a new person. Can you predict if he is a he or she is a she? Well, this is a binary classification problem where you have two categories to classify an observation, and there are various ML techniques to classify this person. One of them is using k-nearest neighbor or KNN algorithm. You can calculate Euclidean distance of the new point with every other available example point. Euclidean distance is nothing but a fancy way of showing distance between points in n-dimensional space. Now if we have set k equals 3, then we choose the 3 nearest points to the new observation, which are these 3. Now you can classify the unknown as the category which has maximum number in that neighborhood. Here we have 2 males and 1 female, so we classify him as male. Simple and intuitive, right? Well, not so much, because actually it looks something like this, where height in meters is small and in a very narrow range, while weight in kgs is in large magnitude and more spread out. Now use k-means to predict gender. If k equals 3, then by KNN it is 100% male. In this, we didn't consider the fact that height of this person is smaller than the smallest of male, and if it was up to height, he would have been a she. What happened here is that our algorithm got biased towards weight. In general, distance-based models will be biased towards high magnitude variables. So what is the solution? Well, scale them so that they look something like this, right? So there you go. You have another reason to scale your features, particularly when you are employing distance-based models. And of course, do it to make gradient descent faster. So there you have. You now know what most people don't know. Now go and scale your features after subscribing to this channel. Thanks for watching and stay tuned for more.